Alright, this is Kenneth Rosever. We're talking about the central limit theorem, and we're going to do a problem from your book. It's example 615. For those of you who might not be in the class, this is taken from page 334 of Blumen's 5th edition Elementary Statistics, a step-by-step approach, published by McGraw-Hill. Okay, anyways. So on that page, he gives this example: meat consumption. The average number of pounds of meat that a person consumes per year is 218.4 pounds. So that's how much I weigh, about, I don't know. Assume that the standard deviation is 25 pounds and the distribution is approximately normal. And what I like about this example, and the reason I chose it, is because there's actually two parts to it. First part, find the probability that a person selected at random consumes less than 224 pounds per year. So they've already told me that the distribution is normal. And now they want me to find the probability that a person, I stop there because that's important, that a person selected at random consumes less than 224 pounds per year. So let me insert a picture really quickly here. But first, I don't want that picture to go in anywhere. Let's have it pop in down there. Okay, insert a picture. Alright, here's my picture. I always like to have a picture because I feel like when it's there, I can see what's going on. So, first thing First thing is I'm going to fill in this picture with a little bit of this information. It says the average number of pounds of meat that a person consumes per year is 218.4 pounds. So, based on that, right here, in the center, is my mean, and that is 218.4 pounds. I'm allowed to use this bell curve because they told me the distribution is approximately normal. Furthermore, I actually know where this one standard deviation line is because I can add 25 to that and get, 243.4. I think that's right. Yeah. But I'm just going to write this. The standard deviation of this is 25 pounds. Now, based on that, since part A is only interested in a single person, I don't use the central limit theorem on this. I just go, here's the z-score. It's they want less than 224, so my value of interest, which is the cutoff value, is 224 minus 218.4 divided by 25. And when you do that and do the math on it, you get 0.22. And if you have 0.22, then you can then go to the table and look up 0.22. But before we do, we need to know a little something more. So it's clearly to the right of the mean, but we could tell that just by looking at 224. But they want to know, what is the percent that or probability that a person selected at random consumes less? They want the lesser side. So that is the left tail, which is good because that's how our table's set up. It's set up to give us left-hand areas. So I am going to be over here on the right because I'm looking for a value that is on the right of the mean. It's a positive value, and specifically it was 0.22. So 0.22? Yeah, 0.22. So I'm up here in the 0.2 row and the O2 column, and my answer is 0.5871. So that was pretty easy. Oh, whoops, I don't want that. Sorry, I'm all discombobulated. So my answer is P of consumption less than or equal to 224 pounds, which is the same as P of Z less than or equal to 0.22 is, no, I forgot it already, 0.5871. 0.5871. That's the probability. Now, if a sample, this is part B, if a sample of 40 individuals is selected, find the probability that the mean of the sample will be less than 224 pounds per year. So now we're looking at the mean of a sample, and we want to know the probability that that'll be less than 224, but we're dealing with a sample, not a person. So it's different. In fact, it's very, very different. Because now what was the standard deviation is no longer the standard deviation. Let me do this. Now our curve is going to be significantly more compressed. I need to grab this, I think. Okay? Because the standard deviation is going to be a lot smaller. It's going to be about 1/6 as big. How do I know that? Because, well, the mean is still, what? It's still the same. It's still 218.4. But now the standard deviation for the sample means, also known as the standard error, is going to equal the population standard deviation divided by the square root of n. And that is 25 divided by the square root of 40, which is a little more than 6. So this is going to be a little less than 25 divided by 6, whatever that is. And if you, I don't know what that is off the top of my head, but I do know if we now try to find the z-score of 224, we can no longer use the z formula we used a second ago. We have to use the central limit based z formula, which is for sample means. And so we use the one that looks like this. Okay. This would still be 224. This would still be 218.4. But now on the bottom, we're dividing by 25 divided by the square root of 40. Note, when you divide by a fraction, you can also multiply by its reciprocal. So this could also be thought of as the square root of n times x minus mu over sigma. That's another way you can write this formula. They don't do it that way because it's easier to remember in this form, because it's just a slight change from a formula you already know. And when you do that out, your answer is the z-score is 1.42, which means now that 224 is somewhere way over here with respect to the means, and using 1.42 and looking that up in the table, we see here's 1.4, here's 1.42, it's 0.922. 9222, so 92.22%. So our answer now, and that's P of x bar being less than 224, which is the same of P of z being less than or equal to 1.42, is 0.9222. And that's our answer. Okay, let me check my time. I probably don't have time to do an ALEKS one, so I'll stop it there, and I guess this will be a 4-parter. Oh dear Lord. Okay, that's it for this one. Bye.